Good morning, friend. This is the design of the PMOS. We know PMOS is three-terminal device. One terminal is called drain, second terminal is called gate, and third terminal is called source. We know threshold voltage of PMOS is less than zero. It means that when the signal at the gate terminal is high, that is VGS equal to VDD, then PMOS is off and it acts as a open circuit. So this is the equivalent circuit diagram of the PMOS when the signal at the gate terminal is high. So if the it acts as an open circuit, then drain is isolated from the source. So if we observe output at the source terminal, then output is independent of the signal at the drain terminal. It remains constant. Now, when the signal at gate terminal is low, that is when VGS equal to 0, then PMOS is on and it acts as a short circuit. Means it acts as a short circuit and output at the source terminal is same as the signal at the drain terminal. So this is the PMOS. Now we have to fabricate PMOS. To fabricate PMOS, we have to design layout. So this is the layout of the PMOS. To fabricate PMOS, we require N-type substrate and P-type active material. So here we design layout by using the lambda rule. So by using the lambda rule, this is the so the minimum size of the contact is 4 lambda. So this is the 4 lambda. Again, separation between contact, and this is the polysilicon for the gate terminal. So the separation between contact and polysilicon is 2 lambda, minimum 2 lambda. If it is less than 2 lambda, then it shows error. Then minimum width of the polysilicon is 2 lambda. So this is the 2 lambda. Again, separation between the polysilicon and contact is 2 lambda, and the again size of the contact is 4 lambda. So this is the 4 by 4 lambda. Now height of the polysilicon above the active material is 3 lambda, and this is also 3 lambda. So total is 14 lambda. 4 plus 2 6, 6 plus 2 8, 8 plus 2 10, 10 plus 4 14. So this is 14 lambda, and so size of the active material, this P type active material, this is the minimum width is 4 lambda and minimum length is 14 lambda. Right. So now we have to design this layout in the Microwind. So this is the Microwind software. Just we have to close this and we have to open new file. This is the this is the scaling 1 lambda, and just we have to zoom out. This is the zoom. Now we have to just make it. So to fabricate PMOS, we required P plus diffusion active material. So here is the P plus diffusion active material. So just we click on this. Minimum width is 4 lambda. So minimum width is 4 lambda, and minimum length is 14 lambda. So minimum length is 14 lambda. So see, 14 by 4 lambda. Now we have to create the contact for the drain, source, and gate terminal. So this is the P type active material. So we use P plus contact. So this is for the drain and this is for the source. We check rule design check error step by step. So this is design rule check error. By using this we can check error. If we click on this, then if there is no error, then it shows no error. If there is error, then it shows error. Right. So right now there is no error. Now we have to use the polysilicon. What is the size of the polysilicon? Minimum width is 2 lambda and height of the polysilicon above the active material is 3 lambda. Here we make 1 lambda. Right. Now we click on the DRC error. See, DRC minimum width is less than 2 lambda. It shows error. So we have to make we just delete this by gun. We can delete this and we make polysilicon is height is 3 lambda and width is 2 lambda. Now we click on DRC error. So it shows no error, means there is no error in the design. Now we have to just add the signal at the drain terminal and the gate terminal. Just so this is the clock we have to add, and we name it as VD. Why D? Because signal at the drain terminal. Just assign it. Now we have to add another clock at the gate terminal, and we name it as a VG and just assign it. Now we have to observe output. We use this visible node. Just click on this and just click on source terminal. Make sure that this is visible in sim. If not in simulation, then it shows no error. Just make it as a visible in sim and just make it as a v out and just assign it. Now we have to observe output. Right now we have to observe output. So to observe output we have to run this, run simulation. Just run simulation. This is our waveform. This is the signal at the drain terminal, this is the signal at the gate terminal, and this is our output at the source terminal. We see that when the signal at the gate terminal is low, and it acts as a short circuit, and output is same as the drain. So in this period gate is low, so in this period, for half time period, drain is low, so it is low, and for the half time period drain is high, so it's high. After that gate becomes high, signal at the gate terminal becomes high, and we know that when the signal at the gate terminal in PMOS is high, then it acts as an open circuit and output remains constant, so output remains constant. Now when the signal at the gate terminal becomes low, and the signal at the drain terminal is also low, so output becomes low again. In this period again, signal at the drain terminal becomes high, so output becomes high. In this way it repeats the cycle. So this is the design of the PMOS. In the next video we will see the design of the CMOS, NAND gate, NOR gate. Thank you.